In this lesson, we're going to see how we can find the volumes of solids of revolution by using the disk method and revolving around either the x-axis or the y-axis. So regions can be rotated around either the x-axis or the y-axis to create a solid which will have a volume. So if I were to rotate this picture right here around the y-axis, it would produce this three-dimensional cone. And if I took this shape and I revolved it around the x-axis, I would get this sphere type shape. So with volumes of revolution, the cross sections will always be a circle. So this is very closely related to finding the area between curves as well as finding the volumes of solids with perpendicular cross sections. So here's a function f of x, and we can see that the area underneath this curve would be from f of x to the x-axis. We could find the volume of a three-dimensional figure using cross sections, but if we use cross sections that are circles, that would indicate that we have a revolution around the x-axis. So the cross-section would be a circle with a radius of f of x, and then it would create this 3D solid. So let's look at just kind of an animation of what this would actually look like. So if we look at this image here, this is again a three-dimensional image. So right now here's the xy plane in 2 dimensions, and we have a graph of this black function here is ln of x, and it's going between 2 and 4 right now. So I'm going to rotate it, whoops, so we can see it kind of looking almost 3D. So if I were to revolve this around the x-axis, I can see that it's rotating around the x-axis, and then it's creating this 3D shape, and these cross sections are circles. So let me just do this one again. Here we go. As it's rotating around the x-axis, it will create a 3D shape. So thinking about this in terms of integrals, the cross section that we have that's a circle, we can see that the radius of the circle is going to be the distance from f of x to x. So the radius of the circle is just the function minus 0 because it's the x-axis. And in this case, we're rotating it around the x-axis. So we're going to be using a to b, which is our farthest left x value for our lower limit, and then b is our rightmost x value for our upper limit. And when we take this to find the volume, it's, remember, going to be the area of x times dx. And the area of the cross section is going to be, since it's a circle, area is going to be pi r squared. Okay, so let's look at this. So if the region is rotated around the x-axis, the volume is going to be pi times the integral from a to b of r of x squared dx. And this is just the radius. Okay, so if I were to have a graph, I'm just going to make this up. So let's say my graph looks like this. If I wanted to bound it between, I'm just going to bound it here. So there we go. So this part of the graph, if I rotate it around the x-axis, it's basically going to look like that. And then each of my cross sections is going to be a circle. That looks really terrible, so I apologize. And that's going to be a circle. I'm trying to make like a three-dimensional circle. And each of these circles, in this case, will have a width of dx, since we're rotating it around the x-axis. If I'm rotating it around the y-axis, the volume will be pi times the integral from c to d, which is going to be our lowest y value, and d is going to be our highest y value, r of y squared dy. So again, this is going to be the radius, but it's going to be in terms of y. So if I had a shape like, let's say this, and I'm bounding it here, so I'm just going to connect it this way. So if I take this shape and I rotate it around the y-axis, it's going to look like that. And my cross sections of circles are going to look like this. Oops, that's a three-dimensional circle, if you can see that. And in this case, the width of each of these circles is going to be dy. So let's look at this example. So find the volume of the solid created when the region enclosed by y equals x squared, the x-axis, and the lines x equals 0 and x equals 2 is rotated around the x-axis. So first thing we want to do is just sketch this out, and I know it's very hard to draw this, but just kind of visualize it real quick. So we have y equals x squared, but it's bounded by the x-axis, x equals 0, and x equals 2. So it's going to be basically this piece right here. So this top curved piece is your y equals x squared. It's not going to go past y equals 0 or x equals 0 or x equals 2. So we're bounded right here. If I were to rotate this around the x-axis, it's going to, look like that on the other side. Just visualize this. And then our cross sections are circles. So it's going to look like, I'm not a good artist. I'm sorry. There we go. Something like that. So we know that the area that we're using is pi r squared, right? And for all of these problems, we're going to use pi r squared for our area because all of these are going to be circles. R, which is our radius, is going to be x squared because that is the top function, which is this x squared, and it's stopping at x equals or y equals 0 on the x-axis. So when we are rotating it, right, it creates this full circle. The radius is going to be half the circle, so it's just going to be the function minus 0. So our area, write this over here, is going to be pi times the radius, which is x squared, squared. So our area will be pi x to the 4th. So our volume, I'm going to pull out the pi because that's my constant. So the volume will be pi times the integral from a to b, so farthest most x value, which in this case is 0, and then the farthest right x value, in this case it's 2. So we're going to go from 0 to 2 of x to the 4th dx. So now we're just going to take the antiderivative. So I'm going to keep the pi over there on the outside, take the antiderivative of x to the 4th, so we get 1/5 x to the 5th, and then we're evaluating it between 0 and 2. So we just want to plug in 2 for x, and then plug in 0 and subtract them. So this would give us 32/5 pi. All right, so let's look at another example. So find the volume of the solid created when the region enclosed by y equals the square root of 9 minus x squared. The x-axis, the lines x equals 0 and x equals 3 is rotated around the x-axis. Okay, so if I were to kind of graph what this is going to look like, this is going to be like something like that. All right, so this curve that I drew is the square root of 9 minus x squared, and then we're bounded here by x equals 0, y equals 0, which is our x-axis, and then this is 3, right? So there's really like this like line going this way. So if I were to rotate this around the x-axis, it would be, that's really bad. Something that's not as bad as that, but something similar to, I don't know, like that. And again, your cross sections are circles, so we're looking like that. So here, again, we know the area we're using is pi r squared because for all of these we're using that. Our radius is going to be the square root of 9 minus x squared. So our area will be pi times the square root of 9 minus x squared squared, which is just going to be 9 minus x squared times pi. So for our volume, we're going to pull out that pi because that's our constant. From x to x, we're going from 0 to 3. So 0 to 3 is going to be our limits of integration. And then we have 9 minus x squared dx. Okay, so again, just take the antiderivative. So we'll keep that pi on the outside. Antiderivative of 9 minus x squared, we'll get 9x minus 1/3 x to the 3rd. And then we plug in 3 and 0 and subtract them. And if we do that properly, we should get 18 pi. Okay, so now we're going to look at rotating around the y-axis. So find the volume of the solid created when the region enclosed by y equals x squared, the y-axis, and the lines y equals 0 and y equals 4 is rotated around the x-axis. So first thing we have to figure out is what this is going to look like. So y equals x squared, but it's bounded by x equals 0, y equals 0, and y equals 4. So I'm just going to put 4 up there for that's y equals 4, this line here, right? And y equals x squared is going to look like this shape, but I'm cutting it off because that can only be bounded in this region right here. So if I rotate this around the y-axis, I'm going to end up with something that looks like that on the other side. And my circles are going to be drawn horizontally now. So it's going to look something like that. Because we're doing this around the y-axis, everything needs to be in terms of y. So the problem that we have here is that our function is in terms of x. So we have y equals x squared. So we need to change that to be x equals something with y. So if I solve for x, I have to take the square root. When I take the square root, I do get plus or minus the square root of y. However, looking to see where this is, because it's in the first quadrant, we know that it has to be the positive version. So x is going to be the square root of y. So for the area, again, we're using pi r squared. So we're going to have pi times the radius squared, and the radius is going to be the square root of y. So we have the square root of y squared. So our area will just be y pi. For our volume, we're going to pull out the pi since that's our constant. And now we're going from the lowest y value to the highest y value. So we're going to go from 0 to 4. And then our area is just going to be y dy. And again, we're just going to take the antiderivative. So I'm going to keep the pi on the outside. I'm going to take the antiderivative of y. So I get 1/2 y squared. And then we're going to evaluate it from 4 to 0. So we're going to plug in 4, plug in 0, subtract them. So if we do that properly, we should get 8 pi. Okay, and let's look at one more example. So find the volume of the solid created when the region enclosed by 2x equals y squared, the lines x equals 0 and y equals 4 is rotated around the y-axis. Okay, so again, I'm going to sketch a little picture of this. So I have, if I were to, let's say, solve for y, I would have a square root function. So my graph looks something like this for this 2x equals y squared. It's going to look something like that. It's bounded by x equals 0, so it's bounded by the y-axis. It's bounded by y equals 4. Oops. Okay, and then it is rotated around the y-axis, so it's going to look something like, oops, like that. Again, pretend it looks halfway decent. And our circles are going to be, again, horizontal because it's rotating it around the y-axis. So again, if we're doing this in terms of y, we have to get x equals. So we're pretty much almost there with this function. We just have to divide by 2. So x is going to equal 1/2 y squared. So our area is going to be pi times the radius, which I'm just going to put equals r, right? That's going to equal our radius. So 1/2 y squared. So our area will end up being, actually, let me put the pi at the end. So it's going to be 1/4 y to the 4th, pi. So for the volume, we're going to pull out the 1/4 and the pi because those are both constants. So 1/4 pi comes outside. Because we're doing this in terms of y, we're going to have the lowest y as my lowest limit of integration, so that's going to be 0. Highest y value is my upper limit of integration, that's 4. And then we have y to the 4th dy. So we're going to take the antiderivative, so I will keep that 1/4 pi on the outside. The antiderivative of y to the 4th is going to be 1/5 y to the 5th. And I'm going to plug in 4 and 0 and then subtract them. If I do this properly, I should end up with 256/5 pi.